In this program you are about to see, we are going to show you carbon dioxide or metal arc gas welding, the accessories and equipment used for that, and the various types of positions and joints used to join ferrous and non-ferrous materials. The mag welding is an arc welding process. In this process, the source of heat is an arc formed between a consumable metal electrode and workpiece. Fusion welding of metal plates in sheets is the best method to join metals, because in this process, the welded joints will have the same properties and strength as the base metal. Now, to achieve this, the molten metal must be protected from the atmospheric oxygen, hydrogen and nitrogen by a perfect shielded arc and molten puddle so that they are not absorbed by the molten metal. A shielded arc is formed between the base metal and a bare wire consumable electrode fed continuously through the torch. The shielding action is done by passing an inert gas such as argon, helium and carbon dioxide through the welding torch or gun. It is called shielded metal arc welding or SMAW. As an inert gas is used to protect the arc produced by a consumable metal electrode, this process is called gas metal arc welding or GMAW. It is also known as metal inert gas welding, MIG welding, or metal active gas, MAG, or CO2 welding. When carbon dioxide is used for shielding purpose, it is not fully inert and becomes an active gas partly. That is why CO2 welding is called mag welding. Here, the shielded arc between the bare wire electrode, molten filler metal and base metal is formed by flow of carbon dioxide gas passing through the welding torch or gun. CO2 welding can also be used for welding carbon, silicon and alloy steels, stainless steel, aluminium, copper, nickel and its alloys, titanium and many more materials. CO2 welding is also used in light as well as heavy fabrication work. It has been successfully used in shipbuilding, fabrication of pressure vessels, automobile and aircraft industries. Now, let us see the equipment and accessories for carbon dioxide welding. Power sources for the power supply, wire feeder, carbon dioxide gas cylinder and heater, regulator, flow meter, torch or gun. The most suitable power source for mag welding are DC generator or transformer rectifier, producing constant potential direct current supply. Direct current reverse polarity or DCRP is used for stable arc and smooth electrode metal transfer, deep penetration and excellent cleaning action. The wire feeding mechanism automatically drives the electrode wire from the wire spool fixed inside to the gun. The arc control on the panel can be adjusted to vary the wire feeding speed. Carbon dioxide is a liquid gas which is not suitable for welding. It has to be converted to gas. Therefore, a heater is attached to the cylinder for converting liquid carbon dioxide to gas form. The regulator indicates the pressure of gas flowing from the cylinder and helps to regulate the pressure of the gas flow into the flow meter. The flow meter indicates the pressure of gas required for the welding. The flow of gas can be adjusted on the flow meter depending on the material thickness. The torch or the welding gun delivers the electrode wire, the shielding gas from the wire feeder, and also welding current from the power source to arc area. Let us now see what we have learned so far. We have understood what is gas metal arc welding or GMAW and steel metal arc welding, that is SMAW. The source of heat is an arc formed between a consumable metal electrode and workpiece in mag or CO2 welding processes. Use of CO2 and inert gas in mag welding, application of CO2 welding, equipment and accessories used for CO2 welding. Welding method. The welding is done by forehand or backhand welding technique. In forehand welding, the tip of the electrode points in the direction of the travel. This method is also called as forward or pushing welding technique. This method is best suited for thinner sections. In backhand welding technique, the tip of the electrode points away from the direction of travel. This method is also called as backward or pulling welding technique. Backhand method offers the best penetration and is more suitable for thicker sections.
Let us now see the different types of welding positions. Downhand or flat position, vertical position, horizontal position, incline position, overhead position. In this program, we are going to learn about downhand position, vertical position, and horizontal position. Sequence of operations. Marking, cutting, filing, tack welding or assembling, full welding, finishing, evaluation or quality control. The different types of joints we are going to learn: butt joint, T-joint, lap joint, corner joint, edge joint.
Types of metal transfer. The transfer of metal is achieved by three methods: spray transfer, globular transfer, short circuit transfer. Spray transfer. In spray transfer, very fine droplets of the electrode wire are rapidly projected through the arc from the end of the electrode to the workpiece. Spray transfer requires high current density. Globular transfer. In globular transfer, only a few drops are transferred per second at low current values, while many drops are transferred at high current values. This transfer occurs when the welding current is low. In short circuit transfer, as the molten wire is transferred to the weld, each drop touches the weld puddle before it breaks away from the advancing electrode wire. The circuit wire is shorted and the arc is extinguished. Now this is very helpful in welding thinner sections with great ease and is highly practical in welding on all positions. These are the parameters now for the welding process for GMAW or CO2 welding: arc voltage, electrode size, welding current or rate of wire feed, arc travel speed, stick out, electrode position, welding position, shielding gas. Arc voltage. Now this is a very important variable in CO2 welding process, mainly because it determines the type of metal transfer by influencing the rate of droplet transfer across the arc. Now, the arc voltage depends on base metal thickness, type of joint, electrode composition and size, shielding gas composition, welding position, type of weld, and other factors. Electrode size. Best results are obtained by using the correct wire size for the thickness of the metal to be welded and the position in which the welding is to be done. Remember, the electrode wire should be of the same composition as that of the material to be welded. Basic wire diameters are 0.8 mm, 1 mm, 1.2 mm, 1.6 mm and 2.4 mm. Welding current or rate of wire feed. The wire feed speed will control the current. A wide range of current values can be used with each wire diameter. This permits the welding of metal at various thicknesses without having to change the wire diameter. The current selected should be high enough to achieve the desired penetration and low enough to avoid undercutting and burn through. The success of CO2 welding is due to the concentration of high current density at the electrode tip. Arc travel speed. The linear rate with which the arc moves along the joint, known as arc travel speed, also affects weld bead size and penetration. If the travel speed is lower, the weld pool becomes larger and shallower. As the speed increases, the heat input rate of the arc is decreased. Therefore, there is decreased penetration and a narrower weld bead. If the travel speed is excessive, undercutting occurs along the weld bead because the deposition of the filler metal is not sufficient enough to fill the parts melted by the arc. Stick out. This is a welding gun. Stick out is the distance between the tip of the nozzle and the tip of the electrode. Now, if the stick out is too short, excessive spatter will deposit itself onto the nozzle, restrict the shielding gas, and in turn cause porosity in the weld. Recommended stick out is 6 to 13 millimeters for a short circuiting arc and 13 to 25 millimeters for a spray transfer arc. Of course, generally the distance between the work and the nozzle should be 16 to 19 millimeters. Electrode position. In all welding processes, the position of the gun and the electrode with respect to the joint affects the weld bead shape and penetration. The welding can be done either in the forehand or forward technique or the backhand or backward technique. Gun angles are usually maintained between 10 to 15 degrees.
Welding position. Spray type technique is restricted only to making butt and fillet weld in the downhand position. When used for horizontal fillet welds, this technique tends to give unequal leg lengths, convexities, and undercutting. For welding thin sheets in downhand position, spray type arc may give weld burn through. Vertical and overhead welding is usually carried out with short circuiting metal transfer.
Shielding gas. CO2, the shielding gas, has higher thermal heat conductivity than argon. It requires a higher voltage than argon. CO2 being heavy covers the weld well, therefore less gas is needed. CO2 is even cheaper than argon. The beads made in CO2 have a good contour, they are wide, they have deep penetration and no undercutting. Now within the CO2 atmosphere, the arc is very unstable, resulting in excessive spatter. However, this can be reduced by holding a short arc. Deoxidizers like aluminium, manganese and silicon are used. These deoxidizers remove the oxygen from the weld metal And remember, when using pure CO2, good ventilation is needed.
The chart shown mentions the details. For material thickness of 1 mm, the wire diameter is 0.8 mm, welding current 60 amps, arc voltage 80 volts, wire speed 250 centimeters per minute, welding speed 45. For material thickness of 1.6 millimeters, wire diameter 0.8 mm, welding current 80 amps, arc voltage 18 volts, wire speed 340 centimeters per minute, welding speed 60. For material thickness 3 mm, wire diameter 0.8, welding current 120, arc voltage 20, wire speed 550, welding speed 45. For material thickness 6 mm, wire diameter 1.2, welding current 150, arc voltage 20, wire speed 325, welding speed 25. For material thickness 10 mm, wire diameter 1.2, welding current 150, arc voltage 20, wire speed 325 centimeters per minute, welding speed 15. For material thickness 20 mm, wire diameter 1.2, welding current 150, arc voltage 20, wire speed 325, welding speed 15. For material thickness 20 mm, wire diameter 1.6, welding current 160, arc voltage 22, wire speed 190, welding speed 15. For material thickness 40 mm, wire diameter 1.2, welding current 150, arc voltage 20, wire speed 325, welding speed 12. For material thickness 40 mm, wire diameter 1.6, welding current 160, arc voltage 22, wire speed 190, welding speed 12. For material thickness 75 mm, wire diameter 1.6, welding current 160, arc voltage 22, wire speed 190, welding speed 8. Safety in GMA or CO2 welding. The general safety precautions for CO2 welding are: adequate eye protection should always be worn. If welding for long periods, flash goggles with a number 12 lens shade should be worn under the arc helmet. A number 11 lens is recommended for non-ferrous GMAW and number 12 for ferrous GMAW. All welding should be done in booths or in areas protected by curtains. This is done to protect others in the weld area from arc flashes. Base metal preparation. Identify the metal you are about to weld. Before starting the welding of ferrous or non-ferrous metal, it is very important to clean the edges and welding area from rust, dust or dirt, oil and grease if any. Metal surfaces are generally cleaned mechanically or chemically. Abrasive cloth or wire brushing may be used. For cleaning severely corroded areas, grinding may be used. The cleaning process for carbon dioxide welding or gas metal arc welding is same as the shielding metal arc process. Based on the metal thickness, select a copper-coated mild steel filler wire or CCMS. Let us now prepare the machine setting for welding. Fix the selected filler wire spool inside the welding machine. As per the diameter of the filler wire, the guide roller is selected. It is important to ensure that the size on the tip and the groove are same as the wire size, and it is centered on the roller groove and properly aligned. Otherwise, the groove does not allow the free movement of the wire. Do not tighten the copper-coated mild steel or CCMS wire too hard. Otherwise, there will be a possibility of the copper coating to peel off from the wire. Now, lock the roller groove. Set up a tip matching the welding wire size. Firmly tighten the tip. Check if the tip attached to the welding torch matches the guide or roller groove and also the wire size. Switch on the welding machine. Open the gas cylinder with the help of cylinder key. As CO2 is in liquid form, it passes through the heater and takes the form of gas. Depending on the size of the filler wire, the flow rate of CO2 gas is adjusted on the gas cylinder regulator to flow into the flow meter. The gas passes into the flow meter, where the pressure of the gas is adjusted as per the heat requirement of the filler wire size for forming a shielded arc. Next, adjust the welding current and voltage by adjusting the knob on the welding machine according to the thickness of the materials to be welded or according to the welding position. The distance between the metal surface and the tip of the electrode is called arc length. Adjust the current and voltage individually. If the voltage is too low, the wire sticks to the base metal, generating cracking sounds, and no arc is produced. If the voltage is too high, the wire burns, arc length becomes long, and much spatter is generated. It is also very important to maintain normal arc length of the gun. The wire speed is also maintained depending upon the material or metal thickness. We will move on to do some welding. The first exercise: straight line beads on mild steel plate of 10 mm in flat position. Take the mild steel plate and mark the required dimensions. Hold it in a machine vise. Make sure the marked portion is held away from the edges of the fixed stud. Cut the workpiece to mark dimensions of 10 cm of 100 mm length using a hand saw or a power saw. Let us see the base metal preparation once again before we start to weld. Before starting the welding of ferrous or non-ferrous metal, it is very important to clean the edges and welding area from rust, dust or dirt, oil and grease if any. For cleaning severely corroded areas, grinding may be used. File the job piece properly with a flat file to smoothen the edges. Applying wet chalk on the job piece helps to see the marking better. Remove inflammable or unwanted materials around the welding area. First, fix a 0.8 mm diameter wire spool in position. Pull it through the roller guide to the contact tip of the torch or gun and lock it up. Wear safety apparels like apron, gloves, welding goggles, and welding screen when required. Switch on the welding machine. Turn on the CO2 gas heater as it takes about 5 to 10 minutes for the liquid CO2 to form gas. Before welding, check all the gas joints with soap water to see if there are any leakages in the joints. Check all the machine connections thoroughly and fix the earthing cable. By now, the CO2 gas is also ready. Set the arc voltage at 19 to 21 volts as required for dip transfer mode. The gas flow rate is set at 8 to 10 LPM. Set the feed rate so as to get 90 to 100 amps by striking the arc on a scrap plate. Set the workpiece in a flat position on the table. Hold the torch at an angle of 10 to 15 degrees to the punched line of the workpiece. Open the CO2 gas flow and electrode wire before striking the arc. Strike the arc. Maintain a filler wire stickout of 8 to 10 mm from the end of the contact tip to the job as required for dip transfer mode. Deposit the bead on the punched lines of the job from one end to the other. Weld full length of the workpiece by filling the material in the weld area, moving forward or backward. Here, backward method is being used. Allow it to cool in atmospheric temperature for 5 to 10 minutes. Wear chipping goggles to remove spatters and slag with the chipping hammer. Then, clean the joint using carbon steel wire brush. Check the welded surface for any defect. Let us go through this exercise one more time. Exercise 2. Fillet weld T and lap joint on mild steel plate of 10 mm thickness in flat position. Mark the required dimensions on the mild steel plate as you did before. Now, the workpiece is ready for welding. The welding machine is on. The carbon dioxide gas heater is also on. Arc voltage is set at 19 to 21 volts as required for dip transfer mode. Gas flow rate is 8 to 10 LPM. Mark the center of one plate. The center marked plate is used for the lap joint. Let this be C. Next, mark another plate. Let this be A. To make the base plate B for a T-joint, set plate B on the plate A in the form of inverted T perpendicular or 90 degrees to A as shown here. Feed rate is set to get 90 to 100 amps by striking the arc on a scrap metal. Tack weld on both ends of the T-joint. Set the plate C as a lap joint as shown here on the 75 mm wide plate with T-joint centered on it. Tack weld at both sides of the lap joint as shown here. Keep the tack welded job piece at 45 degrees from the horizontal plane so that the welding can be done in flat position. Deposit the bead on the tack welded job piece from one end to the other. Weld to full length of the workpiece by filling the material in the weld area, moving forward or backward. Let it cool at atmospheric temperature for 5 to 10 minutes. Then, fill the next joint. Remember, the angle between the T-plate and the gun should always be 45 degrees. The angle between the electrode tip and the base of gun direction should always be maintained between 10 to 15 degrees. Once the filling of the second joint is over, let it cool again. Now, deposit the bead again on the back side of the joint as well. Let it cool again. Remove spatters with chipping hammer. Clean the joint using carbon steel wire brush. Check the welded area for uniform flow of filler material. Inspect the welded joints for undercut, porosity, uneven bead formation, edge of the plate melting off, distortion if any, and good bead profile. Check the welded surfaces for cracks using destructive and non-destructive tests. Let us see this exercise one more time. Exercise 3. Fillet weld outside corner joint on mild steel plate of 10 mm in flat position. Prepare the mild steel and mark the dimensions. Cut it, file it, and clean the workpiece to be joined. Particularly the top of the plate, the side walls of the groove, and the underside of the joint. Once this is done, the job piece is ready for welding. The welding machine is on. The CO2 gas heater is switched on 5 to 10 minutes before starting the welding to form CO2 gas as it is a liquid gas. With an arc voltage of 19 to 21 volts for dip transfer mode, the flow meter is fixed as 8 to 10 LPM. Set the feed rate. The same 0.8 mm diameter wire spool is used for welding. Tack weld on both the ends. Hold the gun perpendicular or 90 degrees to the joint and strike the arc at the tack, which is also 90 degrees. Move the torch from one end to the other end of the joint in flat position. Maintaining the angle of the torch at 10 to 15 degrees towards the direction of travel. Weld to full length of the workpiece by filling the material in the weld area, moving backward. Maintain a filler wire stick out of 8 to 10 mm from the end of the contact tip to the job as required for dip transfer mode. As seen in the earlier exercise, let it cool for 5 to 10 minutes. Remove spatters with chipping hammer and clean the joint using steel wire brush as done in the previous exercises. Check the welded area for uniform flow of filler material. Check the welded surfaces for cracks using destructive and non-destructive tests. Let us see this exercise once again. Exercise 4. Butt joint on mild steel plate of 10 mm in flat position. You have already seen the preparation of the jobs. Groove or file a 1.5 mm root face on each beveld as shown. Now, the workpiece is ready for welding. .8 mm diameter wire is used for welding. The procedure for CO2 flow into heater and the welding gun is same as observed earlier. Set the feed rate. The arc voltage is set at 19 to 21 volts as required for dip transfer mode. The gas flow rate is set at 8 to 10 LPM. Hold the gun perpendicular to the joint and strike the arc at the tack. Keep a gap between the joints, otherwise the job may get attached to the base. Open the CO2 gas flow in the gun before striking the arc. Strike the arc, maintain a filler wire stick out at 8 to 10 mm from the end of the contact tip as required for dip transfer mode. Maintain the angle of the torch at 10 to 15 degrees towards the direction of travel. The first deposit of the bead is called the root run. Weld to full length of the workpiece by filling the material in the weld area. Allow it to cool for 5 to 10 minutes and then check for uniform flow of filler material. Repeat the filling process one more time in the second run or the intermediate run. Don't forget, maintain a filler wire stick out of 8 to 10 mm from the end of the contact tip to the job as required for dip transfer mode. Deposit the bead weld to full length by filling the material in the weld area. Cool it and repeat the welding process for the final covering or third run. Remove the spatter as done earlier. Check the welded surface for cracks using destructive and non-destructive methods. Let us look over this exercise one more time. Exercise 5. Fillet weld T-joint on MS plate 10 mm horizontal position. Here, we have the plates made ready after cutting. Set the plate B on plate A in the form of an inverted T as shown here, which you have earlier seen also. Tack weld the two plates on either sides, keeping the T-joint in horizontal position. As seen earlier, for 0.8 mm wire, the arc voltage is set at 19 to 21 volts and the gas flow rate at 8 to 10 LPM. When the plates are ready, mount the plate such that the plate is vertical and the scribed lines are in horizontal position using the job positioner. Feed rate is set. As was in the previous exercise, hold the torch at an angle of 10 to 15 degrees from the base plate and 45 degrees from the T-plate. Deposit the bead from one end of the T-joint to the other in the root run or the first layer. Allow it to cool in atmospheric temperature for 5 to 10 minutes, then continue the second run as shown. Let it cool. Finally, weld the third run. Let it cool. Remove the spatters with a chipping hammer and clean the joint using a carbon steel wire brush. Check the welded area completely for uniform flow of filler material. Test for any cracks or defects using destructive and non-destructive methods. Come, let us see this exercise once again. Exercise 6. Butt weld single V-butt joint on mild steel plate 10 mm horizontal position. You have already seen the preparation of the jobs. Tack the prepared jobs. Tack the job to the metal piece as shown. Mount the job such that the plate is vertical and the scribed lines are in horizontal position using the job positioner. Hold the gun perpendicular to the joint and strike the arc at the tack. Move the torch from left to right end of the joint in horizontal position. Maintain the angle of the torch at 10 to 15 degrees towards the direction of travel throughout the weld length. Deposit the root run of the bead as shown. Weld to full length of the workpiece by filling the material in the weld area. Allow it to cool at atmospheric temperature completely. Check the welded area for uniform flow of filler material. Now, deposit the second run of the bead. Once the second run is over, allow it to cool again. Check the welding area for uniform flow of filler material in the second run, and then repeat the process for the final covering. Once the final covering is over, allow it to cool at atmospheric temperature till it cools completely. remove the spatter and clean the joint. Check the welded area thoroughly for uniform flow of filler material. Finally, check for any defects or cracks on the welded surface using the destructive and non-destructive methods. It is time to look at this exercise one more time. Exercise 7. Fillet weld inside corner joint on MS sheet of 10 mm in vertical position. The welding machine is on. 0.8 mm spool is fixed. The CO2 gas heater is connected to the electric supply 5 to 10 minutes before starting to weld. Set the arc voltage at 19 to 21 volts as required for dip transfer mode. Set the gas flow rate at 8 to 10 LPM. Set the feed rate. Tack weld the job. Mount the job such that the plate is vertical and the scribed lines are in horizontal position using the job positioner. Hold the gun perpendicular to the joint and strike the arc at the tack. Move the torch from bottom to top end of the joint in vertical position. Maintain the angle of the torch at 10 to 15 degrees towards the direction of travel throughout the weld length. Maintain the filler wire stick out. Deposit the bead on the joint of the job from one end to the other. Weld to the full length of the workpiece by filling the material in the weld area, moving upward in forward movement. Allow it to cool completely. Remove spatters and clean the joint using carbon steel wire brush. Check the welded area for uniform flow of filler material. Check for any defects or cracks on the welded surface using the destructive and non-destructive methods. Let us now see this exercise one more time. Exercise 8. Fillet weld T-joint on MS sheet of 10 mm in vertical upward position. By now, you know the preparation of the jobs. Take the prepared jobs. The diameter of the wire spool is the same 0.8 mm. The welding machine is already on. CO2 gas heater is on 5 to 10 minutes before starting the welding. Set the plate B on plate A in the form of inverted T. Tack weld the two plates on either end, keeping the T-joint in vertical position. Arc voltage is set at 19 to 21 volts. Gas flow rate at 8 to 10 LPM. Feed rate Tack a metal piece. Mount the job such that the plate is vertical and the scribed lines are in horizontal position using the job positioner. Hold the torch at an angle of 10 to 15 degrees to the job. Open the carbon dioxide gas flow before striking the arc. Strike the arc maintaining a filler wire stick out of 8 to 10 mm from the end of the contact tip to the job as required for dip transfer mode. Weld to the full length of the workpiece by filling the material in the weld area, moving upward in forward movement. Allow it to cool. Remove spatters with chipping hammer and clean the joint. Check the welded area for uniform flow of filler material. Check the welded surface for cracks using the destructive and non-destructive methods. Let us now see this exercise once again. Exercise 9. Fillet weld outside corner joint on MS plate of 10 mm in vertical upward position. You have already seen the preparation of the job piece. Let's move on to the exercise straight away. 0.8 mm spool is fixed. Set the arc voltage at 19 to 21 volts as required for dip transfer mode. Set the gas flow rate at 8 to 10 LPM. Set the feed rate. Tack weld the jobs. Mount the jobs such that the plate is vertical and the scribed lines are in horizontal position using the job positioner. Hold the gun perpendicular to the joint and strike the arc at the tack. Move the torch from bottom to top end of the joint in vertical position. Maintain the angle of the torch at 10 to 15 degrees towards the direction of travel throughout the weld length. Weld to the full length of the workpiece by filling the material in the weld area. Maintain the filler wire stick out. Allow it to cool completely. Remove spatters and clean the joint. Check the welded area for uniform flow of filler material. Check the welded surface for cracks using the destructive and non-destructive methods. Come, let us go through this exercise one more time. The final exercise of the program. Butt weld single V-joint on mild steel plate of 10 mm in vertical upward position. Take the prepared job pieces. Tack weld the jobs. Mount the job such that the plate is vertical and the scribed lines are in horizontal position using the job positioner. Hold the gun perpendicular to the joint. Maintain the angle of the torch at 10 to 15 degrees towards the direction of the travel throughout the weld length. Maintain a filler wire stick out of 8 to 10 mm for the dip transfer mode. Weld to full length of the workpiece using upward and forward movement. Allow it to cool. Remove the spatters and clean it. Check the welded area for uniform flow of filler material. Check the welded surface for cracks using destructive and non-destructive methods. Come, let us go through this exercise once again. Weld defects, causes and remedies in CO2 welding or GMAW. Defect: difficulty in starting the arc. Possible cause: polarity can be wrong. Remedy: check polarity. There can be insufficient shielding gas. Remedy: try reversing check valves. Poor ground. Remedy: increase the gas flow rate. Open circuit to start switch. Remedy: check ground return circuit repair. Defect: arc may be unstable. Possible cause: cable connection may be loose. Remedy: check and tighten. Weld joint area may be dirty. Remedy: clean chemically or mechanically. Defect: there may be an undercut. Possible cause: current may be too high. Remedy: use lower current setting. Possible cause: welding speed too high. Remedy: slow down. Improper manipulation of gun. Remedy: change angle to fill undercut. Arc length too long. Remedy: shorten arc length. Defect: excessively wide bead. Current too high. Use lower current setting. Welding speed too slow. Speed up welding speed. Arc length too long. Shorten arc length. Incomplete penetration. Faulty joint design. Check root opening, root face dimensions, including angle. Welding speed too rapid. Slow down welding speed. Welding current too low. Increase welding current. Arc length too long. Shorten arc length. Improper welding angle. Correct angle or change gun. Incomplete fusion. Faulty joint preparation. Check root opening, root face dimensions, including angle. Arc length too long or dirty joint. Shorten arc length, clean chemically or mechanically. Porosity. Dirty electrode wire. Hold gas cup closer to work. Dirty base metal. Increase gas flow. Inadequate gas shielding. Decrease gun angle. Check gun and cable for air and water leaks. Shield arc from drafts. Center contact tube in gas cup. Replace damaged gas cup. Keep wire spool on welder covered. Keep unused wiring shipping container. Clean chemically or mechanically.
Let's take a look at some of the advantages and disadvantages of CO2 welding. CO2 welding is economical because of less edge preparation and no stub loss. It produces joints with deep penetration. Both thin and thick material can easily be welded. It can be used for both ferrous and non-ferrous materials like carbon, steel, copper and its alloys, aluminium and its alloys. No solid flux is used, so there's no need to clean up slag after each run. The deposition rate is more, and CO2 welding has been successfully used in shipbuilding, pressure vessels, aircraft and automobile industries. It is ideally suited for mass production, and well, those were some of the advantages. The main disadvantage of CO2 welding is the cost. The equipment is very expensive, complicated and less portable. The welding can only be done within a certain distance from the machine. And this is because CO2 is stored in a cylinder in liquid form. it needs to be converted to gas before it is used. And that is done by passing it through a gas heater which is attached to the cylinder. If the pipe is too long, the CO2 will turn back into liquid form quickly. Some of the other disadvantages are that the air drift might affect the free flow of the shielding gas. CO2 welding might not be suitable for outdoor use. The cooling rates of the weld metal are much higher. And yes, another disadvantage is that CO2 welding is not suitable for general or commercial works. Once the welding is over, remember, it is equally important to shut down all the accessories and equipment. First, release the knob on the gas cylinder. This cuts off the gas flow into the heater and the regulator. Close the gas cylinder. It is very essential for the complete gas in the heater, flow meter, and the cable to be used up completely. Otherwise, once the heater is switched off, the CO2 gas in the heater, flow meter, and the cable turns to liquid form and therefore may damage the equipment and accessories. Let the gas flow out completely by switching on the torch gun. When the gas is used up completely, switch off the welding machine and shut down the power supply. I hope you have understood this program on CO2 welding, and I wish that every process that you have seen on the program will help you in your training and professional work. All the best.